All right. So, this next section that we're going to be entering, okay, good news, all right, we're not going to be learning some new crazy operation. We're still going to be using the derivative, all right. This section is entitled is kind of grouped as the applications of the derivative, okay, how we're going to now use the derivative. And so rather than our main focus being taking the derivative and making sure we're okay with taking the derivative, now it's going to be, we know how to take the derivative, how can we use that in a variety of different situations and stuff like that, okay? One of the main ways we're going to be utilizing the derivative is to kind of explore behaviors of functions, okay? Something you guys have been doing since probably Algebra 1, maybe even before that, right? So in Algebra 1, right, you would have to determine when a function is increasing, when a function is decreasing, when a function is being constant and stuff like that. Well, now we're going to be using the derivative to do that. And calculus to do that. In Algebra 1, you even had to find maybe maximum points and minimum points. Okay, well, now we're going to be using calculus to do that. I know in pre-calculus, when we were doing the curve sketching, we would graph the curves of things and stuff like that, and we would try, we'd do polynomials, and I'd have you for me at least, I'd have you guys find the zeros, and then determine the middle behavior between the zeros, whether you would go up or down between the zeros and stuff like that. And I was saying well, this isn't exact, right? We're kind of finding a maximum, but it's not the actual maximum. Well, now we're going to use calculus to actually find maximums and things like that. Okay, and so today's section is entitled Extrema or Extrema on an interval. Okay, and so we're going to be looking at how to find extreme values. Okay, and not whoa extreme, but maximums and minimums and stuff like that. Okay, so definition of extrema: let f be defined on an interval I containing C, okay? F of C, so f at C is the absolute minimum of f if f of C is less than or equal to f of x for all x values, okay? Whereas f of C is the absolute maximum of f if f of C is greater than or equal to f of x for all x. So in other words, another way to kind of think about this is just the smallest value of f on the interval. Okay? That's what the absolute minimum is. It's just the smallest value of f on the interval. Likewise, absolute maximum is the largest or the greatest value of f on the interval. Okay, the largest or greatest value of f. That's all it is. Okay, absolute, right? Absolute means for sure, kind of thing. It is absolute minimum, absolute maximum. The highest or the lowest, okay? The minimum and maximum of a function on an interval are the extreme values. Collectively, we talk about those as being the extreme values, right? Because the highest and lowest, those are the extremes of the function, right? On the interval. The overall minimum and maximum of a function are called the absolute minimum and the absolute maximum on the interval, right? So again, overall minimum, maximum, absolute minimums and maximums. Okay. Sometimes you could just refer to these also collectively as the absolute extrema. Absolute extrema. All right. So, anyway. Oh, and I think, let's see here. I also wanted to say, these are also sometimes, it's more of an old school way of saying it, but it's also sometimes known as the global extrema. Okay, or the global min or the global max. So again, global being it's kind of the big picture for the whole thing. What is the highest point? What is the lowest point kind of thing? Okay, so also you see the word global, but that's not really used in recent years, but it does show up on some of the older stuff. So I'll throw it out there. Okay, so what we're going to do here, no calculus. Okay, so you can breathe easy, right? No calculus. Not that you should be too tight about anything today. It should be pretty straightforward stuff. But anyway, we're going to find the absolute extrema here. We're just going to take turns identifying here. So let's look at this function first. And we're going to identify what the absolute maximum and the absolute minimum of the function are. Okay? So no trick questions here. I mean, I'm not trying to it is really what you think it is. So looking at our graph here, what is the absolute maximum point? 2, 5. Exactly right. Okay, Mario, how did you determine that it was 2, 5? You looked at the graph and you were looking for what? The highest point. Exactly right. 2, 5. There it is. Okay. What is the absolute minimum of this graph? 0, 1. Okay, because it is what? The lowest point, right? Okay, no trick questions there. No trick questions. All right. Now, we're going to take this same graph. So this was the graph, by the way, of x squared plus 1 on this closed interval from -1 to 2. And now we're going to take a look at the graph, but it's the same function, but now it's on a different interval. It's from the open interval, -1 to 2. So we're not including the endpoints here. Okay? With that change, we're going to have some change in our solutions here too. Let me go to the easier one. What's the absolute minimum of this particular graph? Still 0, 1. Still 0, 1, right? That is still the lowest point right there. Okay? What is the absolute maximum of this graph, though? Okay? Right. And so, Gabe, what do you want to say? So, right, the idea here, or I see what you're trying to say, so good thing, right? We have a problem here in that we have this open circle, right? We can't actually get to this point, but we can approach it. That's the best we can do. The problem with approaching, though, is that we never get to a single value. We can always get closer and closer and closer and closer. Even if it's infinitesimally closer, we're still getting closer. And so we never really approach a single maximum point. And so what we actually say here is that it does not exist. Because there is no single point we can list, we have to say does not exist. Okay, there is not one. Okay, so armed with that information, let's go once again to our third example here and see how things change here. Okay. Do we have an absolute maximum for this function? We do. It is 2, 5. Okay, we have a highest point right here. It's at 2, 5. Okay. Do we have an absolute minimum for this function? You said no? Is that what I heard? Yes, it is. There is no absolute minimum. As we get closer and closer to this lower point here, it's an open circle. So we can keep getting closer and closer and closer, and we never have a single lowest point, and so we have no absolute minimum in this case. Okay? So, in both of these scenarios, we ended up with absolute extrema that did not exist, right? One here because we excluded the endpoints. We excluded the endpoints. And then here, we still had the -1, but the problem was that we had an open circle here, and so at the lowest point, and so it's not continuous there. So we have a new theorem to introduce here, and it's called the extreme value theorem, right? That's what we were trying to find here, extreme values, okay? So what does the extreme value theorem say? There is guaranteed to be an absolute minimum and an absolute maximum for f on a closed interval, AB, as long as f is continuous on the closed interval from A to B. Okay? So here this was an open interval, so we're excluding the endpoints. Okay? So yes, even though this function was continuous, we still couldn't find one because the endpoints weren't included there. Notice again, extreme value theorem. So what are the requirements? It requires that f is continuous on a closed interval. Then you are guaranteed to have an absolute minimum and an absolute maximum. Okay? Guaranteed to have an absolute minimum and absolute maximum. Notice what it does not say. It does not say where those points are. Right? So this is merely an existence theorem. Only proves existence. Just like the intermediate value theorem, right? It only proves that there must be a y value that, between your two, y values at your endpoints. It doesn't say where it is. Same thing here. This only proves that there must be an absolute minimum or absolute maximum. Okay? So this can be a good justification for certain kinds of problems, right? But it doesn't help you maybe answer where those solutions are located. Okay, now, we're going to compare those absolute extrema now to something called relative extrema. Relative extrema. Okay? So these are things that are going to be extreme values, relatively speaking, to the other points around them. Okay? So sometimes relative extrema are also called local extrema. They're like the extrema of their neighborhood. Okay? Local extrema. Okay. But first, we'll identify our absolute extrema, make sure we're okay with that. So, do we have an absolute maximum? And if so, where is it? Anybody? 416, we have an absolute maximum. Do we have an absolute minimum? And if so, where is it? -2, -20. Okay. Notice here also, folks, I'm not abbreviating, okay? And it really pains me to do that because it takes up so much more time to write the words out, I guess, but I want to model good behavior for you because on the AP test, it's not really a good idea to abbreviate. You really want to write out the full words just so that way the grader doesn't like misconstrue whatever you're trying to say, okay? So that's why I'm writing everything out. Anyway, the graph of our function here, okay, we say would have a relative minimum. So where do you think we would have a relative minimum on this graph? Relatively speaking, what does it look? Where might we have that relative minimum? Any ideas? At 2, not -1, 2, -4. Yeah. Watch the units there. I know it's weird that we were jumped to like a, jumping counting by different numbers. But yeah, 2, -4. Okay, because in that little neighborhood of points right here, right, this is kind of like a minimum value, right? We would want to call that a minimum because it is kind of like dipping down and then back up. Okay, so then if that's a relative minimum, where would we have a relative maximum? 0, 0, because you have kind of like a little peak there. Exactly right. Okay. This is that middle behavior stuff that we talked about in pre-calculus, where I said like the best we can do is try and like figure out, midpoints of the zeros, but that's not always where they are. So here we're actually going to be identifying and calculating where these relative minimums and relative maximums are, so you can know how far up, a peak goes or how far down a valley goes. So think of the relative maximum occurring, speaking of those things, think of the relative maximum occurring on a hill or peak, okay, of the graph, and the relative minimum occurring in a valley or trough. Very, very technical mathematical language here. Hill, peak, valley, trough. It's not. I know it's silly, but that's what we call it, right? I mean, that's what it looks like. So that's what we're going to use there. Okay. So let's actually get into this here. All right. Let's actually get into this. So find the value of the derivative if it exists at each of the relative extrema below. All right, so you can look here in our graph of the sine of x. We have our relative extrema already identified for us. We have a peak right here. We have a valley or trough right there. Okay? Now, I wish they had them correct, but of course we know that the peak of the graph of sine occurs at pi over 2, right? And we also know the valley, or the lowest point for the graph of sine from 0 to 2 pi, is at 3 pi over 2, right? So I'm going to include that. So I gave you guys those. Oh, why don't you all go ahead and determine what is the value of the derivative at those two extrema below. So here's the function. Here's the graph of the function. This is sine of x. Find the value of the derivative of sine at those two relative extrema. Okay, so go ahead, take like 30 seconds. Some of you guys might be able to just like look at it and determine what it is. In fact, most of you guys probably can. But if you want to go ahead and calculate it, feel free. That's not a bad idea. And don't feel bad if you look at it and you're like, I don't know how to calculate that. You'll see it and you'll be like, oh, that's what it is. Okay, so Celia, were you able to come up with an answer for the value of the derivative at like pi over 2, for example? What would the value of the derivative be at pi over 2? 0. Very good. Okay, and then how about Stephen? Did you come up with the value of the derivative of f at 3 pi over 2? What'd you get? 0 as well. What? That's right. Exactly right. Okay. We have horizontal tangents there, right? We've kind of like identified these before, right? The slope here is 0. The slope here is 0. Okay. Some of you guys can probably just look at that and see, oh yeah, it's going to be the slope of 0. We don't even have to like do the derivative and plug it in. But at least we can see by the analysis also we get 0 there. Okay. So again, we have a relative, let me do it this way, relative. And so at pi over 2, that's a relative maximum, right? So relative maximum of f at pi over 2, comma 1. And we also have then a relative minimum of f at 3 pi over 2, comma negative 1. Okay? And so we might be like, aha, so it looks like maybe there's a relationship between relative extrema, right, and the value of the derivative at those particular points. Because in both cases here, our relative extrema, the derivative was equal to 0 at those points. AD. Okay? But let's turn the page here. Okay? Now, again, same directions. Let's identify here. Do we have a relative, and I'm going to put some arrows here to indicate that this goes on forever here. Do we have a relative maximum for this graph? Doesn't look like it, right? No hills, no peaks. Do we have a relative minimum for this graph? Yes, we have like a valley or like a trough here. In fact, we do. Where is the relative minimum? Yep, so in fact, we do have a relative minimum. I can confirm that. You'll later, see why. But relative minimum of f at the point 2, 0. Okay. In the earlier problem, at our relative extrema, the value of the derivative was 0 at those points, right? Horizontal tangent lines there. Will we have the same occurrence here? Will the same thing occur here? At the value, at the derivative of our relative extrema there, the relative minimum, will we expect the derivative to be 0 at that point? No. But what will we expect the derivative's value to be? What's that? Does not exist, right? That's kind of a trick question, I guess, because I said value, but really that's not a value. But yes, we expect the derivative to not exist there, okay? Why would we expect f prime of 2 to not exist? What's happening? Yes, we have a sudden change in slope, right? From the left, what's our slope? -1. From the right, what's our slope? +1. And so, we jump suddenly from a -1 to +1. So slope changes suddenly from -1 to 1 at x equals 2. Okay, without a smooth transition. Yes, Morgan.
Is there a difference between calling it like a relative minimum and an absolute minimum?
So, very good question. In this case, could we also call this point an absolute minimum? Absolutely, we could. Yes, this is also an absolute minimum.
So then why weren't these one on the sine graph? Why weren't those absolute minimums?
We could call these as well absolute minimums and absolute maximums.
Okay.
Because they are the highest points of the graph and lowest points of the graph. But let's go up once more to the very first one that we looked at. Our relative minimum that we identified here, is that also an absolute minimum? No, the absolute minimum is down here. Would we call this thing a relative minimum? No. So sometimes relative minimums and absolute minimums are one and the same thing, but sometimes they are not. Okay, and it's important that we differentiate, that we know the difference between the two. Okay, because sometimes they are the same, sometimes they're not. Okay, so it really depends. And I'll show you again. We're gonna get to that point here in just a second. But very good observation there. All right, last thing, go ahead, take like 30 seconds here to graph this piecewise function for us before we go into the actual analysis. So go ahead, take 30 seconds, graph this piecewise function. Okay. So I'll do that too. if you want to, if you're finished graphing and you want to go ahead, you want to jump ahead, feel free to go ahead and see if you can identify if we have any relative minimum values or relative maximum values. Okay, or relative minimums, sorry, not values. Whether we have any relative minimums or relative maximum points here, and if so, feel free to identify their locations. Okay, so again, once you've got that graph down, feel free to go ahead and identify any relative minimums or relative maximums that you think exist there. Okay. Yeah, oh, I see what you're saying. In this case, it's this.
Oh, it's a positive 7. You should see this first graph. I can't graph this.
No. I know, right? Isn't it frustrating sometimes? You sound like mental break.
Right here, this line is the first
Yeah, looks good. Well done.
graph. Here, this line was the first graph.
I thought
But if you think it's 9 to 7, then that would be right.
No.
well, I thought that the x squared minus 1 was all values greater than 2 for whatever reason.
Okay, so there's our graph. And so let's see here. So Lily, can you identify, do we have any relative maximums of G? And if so, where?
What?
Do we have any relative maximums for this function G here? And if so, where is it located? What are the coordinates?
I said yes, I said at
2, 3. Sounds good to me. Okay. And let's go to Ashley. Do we have any relative minimums of G? And if so, where? You got it. Okay. Okay. All right. But of course, we weren't just asked to identify where the relative maximums, relative minimums were. So again, that's a 0, -1 there. We were also asked in these directions to find the value of the derivative at the relative extrema. Okay. So thank you. All right. So what would the value of the derivative be, Sarah, at G, for example? So at the point 2, 3, what would you expect the value of the derivative to be there for G?
I said it does not exist.
It would not exist. Exactly right. So remember, to take the derivative of a piecewise function, you just take the derivative of the individual pieces. So the derivative of x squared minus 1, 2x. The derivative of 7 minus 2x, -2. And then you keep the same arguments, x less than 2, x greater than or equal to 2. Okay. In this case, then, to kind of see this, well, we would look at, kind of like G prime of 2 in a way, and we'll say, okay, well, if we plug 2 into the top here, we're going to get 4. If we plug 2 into the bottom, it's going to be -2. Since these don't match up, right, the derivative does not exist. Or I'll say, like, G prime of 2 does not exist. Okay, and then finally for the relative minimum there, all right, let's go to long. So long, what would you expect the value of the derivative to be at this relative minimum here?
I would say
0. And in fact, we can calculate that exactly. So we'll do G prime of 0, right, because our minimum occurs at the x coordinate 0. We'll plug 0 in. Since we're plugging in 0, we don't have to plug it into the the top piece here because it's 0 is less than 2. So it'll be 2 times 0, which is just equal to 0. And so he's in fact right. Okay, G prime of 0 equals 0. Okay. So note that in each of these examples of relative extrema, the derivative is either blank or blank. 0 or does not exist. Okay? 0 or does not exist. All right, turn the page. Okay, so let f be defined at C. If f prime is equal to 0, or if f prime is undefined at C, then we call C a critical number of f. Critical number. So that's a new vocabulary term, right? So we learned absolute extrema. The highest point is the absolute maximum. The lowest point of the function is absolute minimum. We learned relative extrema today, right? The kind of a hill or a peak. The coordinate at the top of that hill or peak, that's a relative maximum. The point at the the valley or in the trough, the very lowest point, that's called the relative minimum. And now we're talking about critical numbers, okay? And it's when the derivative is 0 or when the derivative is undefined at C. Okay? So, if that's what makes a critical number, just when the derivative is 0 or undefined at C, I want you to go ahead and find the critical values of this function. Okay? So go ahead and do that. Okay? Go ahead and do that on your own right there. So again, if we want to find the critical values, that means we want to know when the derivative is 0 or when the derivative is undefined. So go ahead and take that derivative there. I'll give you like 30 seconds to take the derivative. And then I'll come around and, well, I'm not come around, I'll do it up here. Make sure I'll do it okay there. Or I'll just go really slowly. How about that? So I'll be like, okay. Okay. So go ahead and take that derivative. Okay. All right, so you've taken the derivative. Please look up and check your answer versus mine here. Okay, so this is what I was kind of like alluding to earlier where, you know, our focus last unit was making sure we take the derivative accurately. Now, we still need to make sure we're taking the derivative accurately, right? So when we see sine squared of x, that is a chain rule, right? So the 2 is the outermost function, something squared, so you have to do 2 times the something to the first power times the derivative of what's inside, cosine, and then plus the derivative of sine, cosine. Okay? So this is not like this is not an overly complicated derivative, right? If you had seen this on the test, you might have been like, yeah, okay, easy points maybe, hopefully at least, right? But when it's in the context of like other new stuff now, it can get a little bit, you know, trickier because we're focused on, you know, just making sure we apply the new stuff okay. Well, we still got to make sure we take the derivative accurately, okay? But then at this point, now that we have the derivative, what should we do to then determine the critical values? Set it equal to 0, right? Because what makes a critical number a critical number? It's when the derivative is 0 or when the derivative is undefined. Do we need to worry about when this derivative is going to be undefined? No. Sine and cosine, they're never going to be undefined. There's no like fraction here or anything like that, so no denominator to worry about. And so we're just going to set this thing equal to 0, and that's going to be the only way we get critical numbers in this case. Okay. This is another sticking point on the test for some folks. The very first question, actually. How do we go about solving this equation? Should I subtract cosine over and then divide both sides by cosine of x? No. Factor. Factor. It's equal to 0. We're going to use the zero product property. So 0 equals factor out of cosine of x, 2 sine of x, plus 1. Okay? Which means then that cosine of x equals 0, and 2 sine of x plus 1 equals 0. And so cosine of x equals 0 from 0 to 2 pi, that's at pi over 2 and 3 pi over 2. And then 2 sine of x plus 1 equals 0, that's when sine of x equals negative 1/2. And sine of x equals negative 1/2 at x equals 7 pi over 6, 11 pi over 6. Okay? And it's okay if you need to draw your reference triangles in order to do that stuff, that's fine. As long as you have a system down, you don't need to, you know, to like be able to spout it off like that quick. It'll be helpful if you can become that quick, right? But I can remember being in high school and always being jealous of people that could like come up with stuff like off the top of their head, because I would always have to draw my reference triangles and like use those. I didn't like memorizing it. But now, after being a math teacher for years and years and years, I finally have it memorized. So, but I also can understand, you know, your frustration with seeing other people be able to spout it off real quick, because that was me. Anyway, questions on that? So there's where our derivative is 0. There's where our derivative is 0. Okay? All right, moving on then. So theorem, relative extrema. This is not one that you need to have like, this is not what we're going to like refer back to, right? It's not really named. It's really just saying what it is. So the relative extrema occur only at critical numbers. If f has a relative minimum or relative maximum at x equals c, then c is a critical number of f. Okay? So what must we have? If we have a relative minimum or relative maximum at a point x equals c, then c is a critical number of f. Notice what is not said here. It is not said that if x equals c is a critical number of f, there is not necessarily a relative extrema at x equals c. So just because you find a critical number does not guarantee it's a relative maximum or relative minimum there. We'll learn a little bit later about how to determine whether one exists there or not. Okay, but for right now, suffice to say, if you have a critical number, it doesn't guarantee that that critical number is a relative minimum or relative maximum. But if you have a relative minimum or relative maximum, you know it must be a critical number. Okay, it's kind of like that whole thing, like, you know, every square is a rectangle, but not every rectangle is a square. Every relative extrema is a critical number of f, but not every critical number of f is a relative extrema. Okay, relative extremas are like a specific subset of the critical numbers, and again, we'll talk about like what that be like. Okay, and here's a good counterexample to this, right? F of x equals x cubed. We know what the graph of this looks like, right? Something like that. Okay. We're going to say f of x has a critical value at blank. Well, to find the critical value here, we'll take the derivative, and we'll set that derivative equal to 0, and so it's when x is 0. So f of x has a critical value at x equals 0 because f prime of 0 is 0. Okay. F of x has a relative extrema at blank. Where is this graph of a relative extrema? Trick question. There isn't one, right? So nowhere. Okay. Because, and again, suffice to say right now, we'll be able to do this more specifically later, but for right now it's okay to just say something like because there are no hills or valleys. Okay, there are no hills or valleys for right now. Later, if we were to test you right now, no problem.
No.
But then after the point where we'll learn an actual like analysis and a diagnostic for it. But for right now, it's okay. Okay, baby steps today. All right, so guidelines for finding absolute extrema. So now we're going back to absolute extrema. We're going back to absolute extrema. So yes, we're gonna cover these two as well. This front and back, and then we're done. Okay. But we are gonna finish off here by going back to absolute extrema and getting some guidelines for those. Okay. So to find the absolute extrema on a continuous interval f, of a continuous function f on a closed interval, right? So here again, saying that it's a continuous function on a closed interval, are we guaranteed to have absolute extrema? We are guaranteed absolute extrema by extreme value theorem. Okay, we are guaranteed absolute extrema by extreme value theorem, right? That is the prerequisite. A continuous function on a closed interval. Prerequisite, that means we're guaranteed absolute extrema, okay? But here's our guidelines, right? So step one, we're going to find the critical numbers of f in AB, the open interval AB, and evaluate f at each critical number. And then step two, we're going to evaluate f at each endpoint. So in other words, okay, where can absolute extrema occur? Absolute extrema for this graph, right? The absolute extrema are at the endpoints. Endpoints, right? Lowest point, highest point. Okay. The absolute extrema here, well, the highest point, the absolute maximum, is at an endpoint. Is the absolute minimum at an endpoint? No, it is at a relative minimum, okay? Which you know is also going to be a critical number. All right. So where can absolute extrema occur? Critical numbers, when the derivative is 0 or undefined, or at the endpoints of the interval on which you're examining. Okay? So let's do a little sketch here of this function on the graph from -1 to 2. So -1, 1, 2. Of course, there's 0 there. Okay. So at 0, we're at 0. That's pretty easy. Let's see here. -1 to the 4th is 1, times 3 is 3, and then plus 4 is going to be 7. So 1, 2, 3, 4, 5, 6, 7. So -1, 7. There's that point. 0, 0. And if we plug in 1, it'll be 3 minus 4, so -1. And then at 2, okay, well, 2 to the 4th is 16. Okay, times 3 is 48. 2 to the third is 8. Times 4 is 32. So 48 minus 32 is going to give us 16 there. So, that's going to go off the page here. So we'll just kind of like, I'm going to go like, way up. So base is going to go up. Down like that, and then up here somewhere. Okay. Okay. So the benefit of this is that without using the actual analysis up here, we can already kind of eyeball and see where the absolute extrema are going to be. Okay. So where do we have our absolute minimum? 1, -1, right? 1, -1. There is the absolute minimum for sure. And where do we have our absolute maximum? 2, 16. Exactly right. This point up here, 2, 16. So we already know where they are, but let's follow this analysis here to see, what's actually happening, what's going on. All right. So first we're going to find the critical numbers of f. How do we find the critical numbers of a function? Derivative and what? Equals 0, or where it is what? Undefined, right? But we don't have to worry about that here because it's going to be a nice polynomial function. So the derivative of this is 12x to the third minus 12x squared. Set it equal to 0. So this is number 1, critical numbers. I'll kind of organize this a little bit here. Okay. How do we solve this? Factor. So factor out a GCF of 12x squared. We're left with x minus 1. So we get x equals 0 and x equals 1 for our two critical numbers. Okay. Yeah, you got to go. Okay.
And could you comment for set trade?
Yeah. Okay. Number 2, evaluate f at each endpoint of AB. Okay. So here's what we're going to do. We're going to take 0. We'll plug in 0. So f of 0, we already found that. It was 0, right? F of 1, we'll plug 1 into our function. So that was -1. We got that. And then we'll also evaluate at the endpoint. So f of -1, which we said was 7, I believe, right? And then f of 2, which we said was 16. Okay? So finding the absolute extrema is kind of like identifying all of the candidates, okay, that could be the absolute points. Okay, so in other words, what are the candidates? The candidates are the critical numbers. An absolute extrema can occur at the critical numbers, or the absolute extrema could occur at the endpoints of the interval. So you identify all the candidates. First, we find the critical numbers, and then we evaluate all the candidates. How do we evaluate the candidates? We evaluate them based on their value in the function. 0 in the function gives us a value of 0. 1 in the function gives us a value of -1. -1 in the function gives us a value of 7. 2 in the function gives us a value of 16. If you look at the values here, which one gives us the lowest y value? -1. So the point 1, -1 is the absolute minimum because it is the lowest y value of the possible candidates. Okay? So we get our pool of candidates, pool of possible points where the maximum or minimum could occur. No other place could they occur except at the critical numbers or at the endpoints. And then we evaluate them in the function. It's got to be the absolute minimum of f when it's the lowest value. And then which point gives us the highest y value? 2 at 16, right? And so, 16 value at the coordinate 2. And so 216 is the absolute maximum. Of f. Okay, 216 is the absolute maximum of f. Okay, now one thing I should have answered this question earlier, but are the extrema guaranteed here? I think we kind of did, but were the extrema guaranteed? Is our function continuous on the interval?
Yeah.
Yes, okay. And is it on a closed interval? Yes. So f is continuous on -1, 2 So, yes, I'm going to abbreviate here, by the extreme value theorem, EVT. Okay, sorry, I want the screen there. Okay, F is continuous on 1, 2, so yes, by the extreme value theorem. Okay, we did have extrema guaranteed. All right. So why don't you guys go ahead and try example 5. Okay, don't do the graph if you don't want to, but go ahead and do what we just did. So again, what did we do? Step 1, find the critical numbers. Okay, find the critical numbers, evaluate those back in the original function. And then step 2, take the endpoints and evaluate those as well. Okay, back in the original function. And to see if you can determine those absolute minimums and absolute maximums of the function. You can use your graph to help you afterwards if you'd like. numbers and endpoints of the interval for absolute extrema. Yep, exactly. Yep, just your particular genes. Yep, yep. Because remember, critical numbers occur when the derivative is 0 and the derivative is undefined. What value for x there in my derivative would make my derivative undefined? Because where is my x really located? Right? After I take the initial derivative, you see with the negative 1/3 here. Since it's a negative exponent, it goes into the denominator, so it would be undefined. Because if you remember, critical numbers, most of the critical numbers we've found so far have been when the derivative is equal to 0. But it's also true when the derivative is equal to 6 or is undefined. Two places for 0 undefined. So that's why it's 0 also. Exactly. If any part of your equation is, or any part of your function undefined, you see the whole thing is undefined because you can't figure it out. Because x to the negative 1/3 on the derivative there, that comes to 2 over x to the 1/3. So that if you put 0 in for x, then it's undefined. Right, you can rewrite it so that you can still solve for y is equal to 0, that's okay, but the original derivative would be undefined, you put 0 in it, that's the problem.
As long as it doesn't go into a zero, right?
So, yes, Gabe?
That sucks.
Because if you have absolute extrema, it's either going to occur at the critical numbers or at the endpoints interval. That's it. Like those are the only two places. So why we find critical numbers to get all our possible candidates ended up. Function, right? Because we're trying to find the absolute extrema of the functions. You got to use the function to evaluate which one is which. Okay, so real quick, I want to pause here because I want to also finish up on the last page. There, we're almost there. So take the derivative, right? If we're trying to find critical numbers, take the derivative, set it equal to 0. Okay. To solve this for 0, you have a couple different ways to do it. I added the 2x over x to the 1/3 over, right? Well, first of all, I changed this to x to the positive 1/3, right? 2 over x to the 1/3, like that. Okay? Actually, let me just go ahead and do this while I'm talking from here. That way people on the video can see. Okay? So we set it equal to 0. So we have 2 over x to the 1/3 equals 2. I multiplied the x to the 1/3 over. Okay? Divide both sides by 2. And then cubed both sides. So it's x equals 1. But then also x equals 0. Because remember that critical numbers occur not only when the derivative is equal to 0, right, like we did up here, but also when the derivative is undefined. And the derivative would be undefined if x was 0 right here, right? That would be something over 0. Even though we have this other piece that's okay, 2 minus undefined is still undefined. And so we have our two critical numbers here, okay? And so we evaluate those critical numbers back in the original function because we're trying to determine the absolute extrema of the original function. So we plug them back into the original function, you get -1 and 0, right? We also evaluate our endpoints. F of -1 equals -5. F of 3 equals 6 minus 3 cube root of 9, okay? What's our lowest point here? -5, okay? How are we sure about that, though? What about this 6 minus 3 times the cube root of 9? Okay? What if we didn't have our calculators here and we were trying to figure out, and we were given this number? Okay? How can we go about figuring it out? So the cube root of 9 is just above the cube root of 8, Lily, exactly right. What is the cube root of 8? 2. So if it was 8, it would be 3 times 2, 6. It would be 6 minus 6, and so it would be 0. But since 9 is a little bit more, that means this decimal, the cube root of 9, will be a little bit more than 2. 3 times a little bit more than 2 will be a little bit more than 6. 6 minus something just a little bit more than 6, it's going to be negative. Okay? But now you have to worry about, well, is it going to be so negative that it's more than -5? Well, you could go, you could, I guess, that's a little bit trickier to determine there. But in fact, the -5 is the smaller value. Okay? So the minimum is at -1, -5. Okay? And so what's the maximum value going to be? 0, 0. Okay, 0, 0. All right. So, in summary, the things that we talked about today, the extreme value theorem states that if f is what? Continuous on a closed interval. I'm going to put that continuous on a closed interval AB. Okay. I'm going to put this in, less mathematical terms. If you want the official mathematical definition, it's back earlier notes. If f is continuous on, on the closed interval AB, then there exists an absolute maximum and minimum of f. Okay? The extreme value theorem states if f is continuous on a closed interval AB, then there exists an absolute maximum and absolute minimum of f. Okay? A critical number is when the derivative is 0 or undefined. Okay? Absolute extrema can occur at endpoints of the interval or critical numbers of f. Sure. Critical numbers of the function. I was waiting for someone to say that. Critical numbers of the function. Okay. Relative extrema can occur at... We wouldn't occur at endpoints. They can occur at critical points. Okay? They don't have to necessarily occur at critical points. Okay? Critical points. Or you can also just say like peaks and valleys, or hills and valleys. Okay, for right now, that's the best we can kind of do. We'll don't worry. We'll get into how to figure out. It's not that bad. It's not bad at all. But peaks and valleys, okay? And that's where we'll stop.
I'm okay with hills and valleys.
Hills and valleys. Hill Valley. Isn't that like I feel like that's like the high school for like, no, it's Bayside High. Hill Valley's something. Anyway. Okay, your homework is on a Google Classroom. Okay. Any set requests for today before we all run off? I know that Long said he wanted to be called for a set. So, Katie. Okay, Ariana, you got it. Other set requests, Madison, you got it. Morgan, yes?
Yeah, me and Emma.
Emma, okay. Any other set requests for today? Set requests? Okay. We'll see you, Celia. Take it easy, Kevin.
The cyclic